Welcome to today's presentation entitled Fundamentals of Geodetic Kinematics. My name is Dr. Jim Beatty, and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center Flight Mechanics Technical Team. This presentation is part one of a two-part discussion about fundamentals of geodetic kinematics, and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. Today's presentation is entitled Introduction and Definitions. In part one, today's discussion will cover mathematical relationships for ellipses and why that's important in the discussion of geodetic kinematics. We'll discuss also coordinate frames and definition of terms, because there's many different coordinate frames and types of coordinates used for geodetic kinematics. The equations used for geodetic kinematics, and the equations used for spherical to rectangular position coordinates and vice versa, which is useful in switching back and forth between the different ways of representing positions over an oblate spheroid. In part two of the implementation, to be presented in a different presentation, we'll cover the concepts of sidereal time, summary of World Geodetic Standard 1984 standard constants that are used for the Earth and its moon. We'll also discuss coordinate frames commonly used for modeling of geodetic kinematics, equations for navigation over an oblate spheroid, calculation of great circle distances, and calculation of position and velocity of an object relative to planet-fixed frames. So what is geodetic kinematics, and what do we mean by that? Well, according to Wikipedia, geodetic word is defined as geodesy, also called geodetics, is a branch of earth sciences. It is a scientific discipline that deals with the measurement and representation of the Earth, including its gravitational field in a three-dimensional, time-varying space. Geodesists also study geodynamic phenomena such as crustal motion, tides, and polar motion. For this, they design global and national control networks using space and terrestrial techniques while relying on datums and coordinate systems. For this current discussion, however, we'll limit our discussion primarily to the geometry and kinematics necessary to define the position and velocity of an object relative to an oblate spheroid representation of a planet. And oblate spheroid just refers to the three-dimensional shape created by rotating an ellipse about its minor axis. And oblate spheroids can also be thought of spheres that are flattened at their poles. And the poles are 2 points on the sphere through which the axis of rotation intersects in the case of a planet. Now we'll cover mathematical relationships for ellipses. And the reason we do this is because an oblate spheroid, as described in the previous slide, is nothing more than rotating an ellipse about its minor axis. We begin with a review of some preliminary mathematical relationships for ellipses. The diagram at the right shows a depiction of an ellipse and a coordinate frame designated by the axes x and y, where x is horizontal and y is vertical in the figure. The 2 points that are indicated by the black dots inside of the ellipse are referred to as the foci of the ellipse. F is the primary focus, and F prime is called the secondary focus. For any point P on the ellipse as shown in the diagram, the sum of the lengths from each focus to the point P is constant. In other words, the distances r and r prime, as shown in the figure, is a constant for any point along that ellipse. You might remember that from high school geometry classes, where you could draw an ellipse with a piece of string and 2 fixed points. The equations for an ellipse in rectangular coordinates x and y can be represented as x over a squared plus y over b squared equals 1, as shown in equation 1 at the bottom left of this figure, where a and b are the semi-major and semi-minor axis lengths, respectively, as shown in the figure. Over on the bottom right side of this slide shows the equation of the ellipse in polar coordinates r and theta, where the origin of that radius and theta is the primary focus f. So theta is the angle from the horizontal x-axis up to the line between the focus and some point on the ellipse P, and r is the distance from the focus, from the primary focus to the point P. The equation for the radius r is some constant divided by 1 plus e cosine theta. That's equation 2 shown at the bottom. That constant k is referred to as a semilattice rectum, and e in the equation is the eccentricity of the ellipse, which we'll discuss in the next slide. Using the polar form of the equation of the ellipse on the previous page, we can solve for k, the semilattice rectum, from equation 2 that was presented on the previous slide. If you evaluate this equation at the positive end of the semi-major axis where theta equals 0, then the radius from the primary focus F to the edge of the ellipse is equal to distance a minus c. That's clear to see from the diagram, whereas the major axis length, though there's a total horizontal length of the ellipse, has a length of 2a, so the distance from the center of the ellipse to the edge is a, and the distance from the center of the ellipse to the focus is c, so clearly a minus c is the distance from the focus to the right edge of the ellipse. That's equation 3 in the second bullet of this slide. At the opposite end of the semi-major axis would occur for the angle theta equal pi. At that point, it's easy to show the distance from the primary focus to the leftmost edge of the ellipse is a plus c. So then that's, from the equation above, that would be equivalent to k divided by 1 plus e cosine pi, or since cosine pi is equal to minus 1, that's k over 1 minus e. So using the two expressions, equations 3 and 4, you can solve for k and c. And doing so, you get the semilattice rectum k is equal to the semi-major axis length a times 1 minus eccentricity squared. That's equation 5. And then also the constant c is equal to the semi-major axis length a times the eccentricity. Or, from this latter relationship, equation 6, we can solve for the eccentricity. The eccentricity is nothing more than c divided by a, as shown in equation 7. Or, said in words, over to the right below the figure, you see that the eccentricity is the ratio of the distance between the two foci and the major axis length. That's the primary definition of eccentricity of an ellipse. And you can see, for example, if you were to stretch vertically that ellipse until it became a circle, the points F and F prime, the two foci, would coincide at the center of the ellipse where the x and y axes intersect. At that point, c would equal 0, thereby the eccentricity would be 0. And that's what you have for a circle. It's a special case of an ellipse with an eccentricity of 0. Well, what's the relationship between A and B, the semi-major axis length and the semi-minor axis length? Using the value that we just computed for k, we can rewrite the polar form of the equation for the ellipse as shown as the first bullet here in the equation 8. That is, r is equal to a times quantity 1 minus e squared divided by 1 plus e cosine theta. And recall from the previous slide that the sum of the distances from each focus to any point in the ellipse is a constant. And so that can be evaluated, what that constant value in equation 9 is, by looking again at the ends of the semi-major axis. At the far right, or positive end of the semi-major axis, r is equal to a minus c. And it's clear to see that since the value c is equal to ae, as shown in the diagram, that's clear to see that a minus c is the same as a minus ae, or a times 1 minus e. And then the distance from the secondary focus, f prime, is a plus c, and clearly that simplifies to a times 1 plus e. So then, summing those two together, it's clear that r plus r prime at those specific points equals 2a. So the constant in equation 9, where r plus r prime equals a constant, that constant has now been solved to be 2a. That's equation 10. Now, at the positive end of the semi-minor axis, that's point B as shown in the diagram to the right, we know that r plus r prime is equal to 2a. We also know that r prime equals r for that example shown. And why is that? Well, we see the two triangles in the ellipse there. The triangle from the primary focus F to point B is the hypotenuse of a triangle that has AE as its base and B as its height. Correspondingly, the triangle from the secondary focus F prime to B has a hypotenuse R prime, a base AE, and a height B. Since those two triangles have the same base, each of them is AE, and the same height B, their hypotenuses must be the same. So therefore, R prime must be the same as R, but since R and R prime equal 2A, then each R and R prime must equal A. So then, knowing that, you can solve for B, as shown at the bottom equation on this slide. B is the square root of A squared minus the quantity AE squared. Or simplifying, B is equal to A times the square root of 1 minus E squared. And the form you may commonly see it is shown over on the right just below the figure, and that's the ratio of B to A, or the semi-minor axis length to the semi-major axis length of an ellipse, is the square root of 1 minus E squared, shown as equation 12. What's the relationship between the eccentricity and what's called the flattening ratio? The flattening ratio is commonly used to define ellipses rather than the eccentricity. Recall from the last result on the previous page, the ratio of the semi-minor axis length B to the semi-major axis length A of an ellipse can be expressed as square root of 1 minus E squared. Or you could rewrite that as 1 minus E squared is equal to B over A, that quantity squared. And that's shown as equation 13. By definition, the flattening ratio of an ellipse is just defined as the difference between the semi-major axis length A minus the semi-minor axis length B divided by the semi-major axis length A. Or in terms of the constants A and B, the flattening is equal to A minus B over A. Or that's the same as 1 minus the ratio of B over A. That's equation 14. Combining equations 13 and 14, then it's real clear that in terms of the eccentricity and the flattening, the relationship shown at the bottom of this slide ties the two together. That is, the quantity 1 minus F squared equals 1 minus E squared, as shown in equation 15. And that's an important relationship to remember, because in lots of texts and technical papers that define geodetic kinematics or geometry of oblate spheroids, you will commonly see 1 minus E squared used in various formulas and relationships. A lot of times you will also see the quantity 1 minus F squared instead of that. And you can see from this equation they are the same value. What is the radius of curvature of an ellipse, and why would we be interested in that in the first place? As it turns out, the radius of curvature is very important for being able to convert from spherical coordinates to rectangular positional coordinates, and so that'll set the framework for some of the equations that we'll show later for how to compute those. And I won't show it here because the algebra is a little too involved, but it's not too terribly difficult to actually derive all the constants that I will show later in this presentation from this one relationship alone. So just from pure mathematics, you can dig it out of most math textbooks. The definition of the radius of curvature of an ellipse at any point P, as depicted in the figure there, is denoted by what I call the vector or the distance rho in equation 16. So the radius of curvature rho is equal to the product of r and r prime raised to 3/2 power divided by AB. That's in equation 16. Now let's look at the figure to the right to see what that really represents. Again, showing the ellipse, r is the distance from the primary focus F to the point P. R prime is the distance from the secondary focus F prime to point P. The line kind of drawn right through the center of that triangle is the radius of curvature, and it shows it terminating at some point within the center of the ellipse, not on the horizontal axis necessarily, not on the vertical axis necessarily, but at some arbitrary point in the interior of the ellipse. It also is noteworthy to note that the angles shown there between those two, where the radius of curvature bisects the total angle between the vector from the primary focus F to point P back down to the secondary focus F prime, that angle is equal on each side of the radius of curvature. In other words, the radius of curvature equally bisects that angle. Now again, from equation 10 a couple of slides ago, we showed that the distance from r plus r prime is equal to 2a. So making that substitution into equation 6, you can show that the radius of curvature of the ellipse at point P can be related to the expression shown in equation 17. That's quantity r times 2a minus r raised to the 3/2 power divided by AB. And also at the ends of the semi-major axis length, what's called the equatorial radius of curvature is just represented by equation 18. That's a times quantity 1 minus e squared. Conversely, the radius of curvature of the semi-minor axis, or at the ends of the semi-minor axis, is called the polar radius of curvature, and rho in that case is represented by equation 19, and it's a divided by the square root of 1 minus e squared. And these particular relationships here won't be used directly in the remainder of the presentation today, but they're key, as I said, to computing factors that will be used in the definitions of transformations from rectangular to spherical coordinate representations of positions on an oblate spheroid. The positions of some object relative to the oblate spheroid are commonly defined using either so-called rectangular or spherical coordinates. Rectangular coordinates are just, and you depict them if you want to by x, y, and z, which would be the notation used throughout this presentation. They're just the coordinates relative to coordinate frame with its origin at the centroid of the oblate spheroid, and those can either be fixed relative to the oblate spheroid and rotates with it as the oblate spheroid rotates, or those axes may be fixed relative to inertial space. Typically, there's two forms of that we'll discuss today. The axes that are fixed relative to the inertial space typically has the x-axis pointed towards the vernal equinox, or the first point of Aries in the constellation Aries. The z-axis points along the spin vector of the Earth, and the y-axis completes a right-handed frame. For the rectangular coordinates that are fixed relative to the oblate spheroid, those are usually referred to as Earth-centered, Earth-rotating, or Earth-centered, Earth-fixed, in which case the x-axis, again the centroid is at the origin is at the centroid of the oblate spheroid. The x-axis of the Earth-centered, Earth-fixed frame points towards the prime meridian, or the Greenwich meridian. The z-axis again points through the spin vector of the oblate spheroid, and the y-axis again completes a right-handed frame. When talking spherical coordinates, there's actually a number of spherical coordinates that can be used. They generally refer to latitude, depicted in this presentation by phi, longitude is depicted in this presentation by lambda, and altitude as represented by the variable h. These are relative to a prime meridian plane and an equatorial plane that are fixed relative to the oblate spheroid. And latitude can either be specified as geodetic latitude or geocentric latitude. We will discuss each of those later and define what we mean by those. Longitude can be specified as either geodetic longitude or inertial longitude, where the geodetic longitude refers to longitude relative to the Greenwich meridian if it's referring to Earth, or inertial longitude, which is relative to, again, the x-axis pointing towards the vernal equinox. Geodetic altitude is just the distance of the object above the surface of the oblate spheroid along a direction normal to the surface of the oblate spheroid directly below the object. And the actual planet shape is obviously much more complex than just an oblate spheroid. It has irregularities, it has tidal motion, at least on Earth, and other things that prevent it from being a perfect oblate spheroid. But it represents the mean planet shape and is used in many analyses of motion over the Earth and other planets as well. The next couple of slides will actually show some graphical depictions of some of these coordinate frames that I just described. In this slide, the figure on the right depicts some coordinate frame axes as well as a point P that's located at some point on the surface of an oblate spheroid. And it can be defined relative to two reference frames, as I described earlier, both of which have their centroids, their origins at the centroid of the oblate spheroid. One of them is the Earth-centered inertial frame, or ECI frame. One of them is the Earth-centered Earth-fixed, or ECEF frame. And some people also call that frame the Earth-centered rotating, or ECR frame. Again, as I described earlier, the ECI frame has its x and y axes in the equatorial plane, with the x-axis pointing towards the vernal equinox, or to the first point of the constellation Aries, z pointing towards the mean axis of rotation, and y-axis completes a right-handed frame. That ECI frame is considered to be inertial for the purposes of applying Newton's laws of motion. The ECEF, or also called ECR frame, has its x and y-axis in the equatorial plane, with the x-axis pointing towards the prime meridian, and on Earth that would be the Greenwich meridian. The z-axis again pointing towards the mean axis of rotation, the y-axis completing a right-handed frame. That ECF, or also called ECR frame, rotates with the Earth at what is assumed to be a constant rate. The parameters that are shown on this figure here that describe the geodetic latitude, the geodetic longitude, and what's referred to as sidereal time are depicted. As you see, the rotation about the z inertial axis that would orient the meridian containing point P is the sum of the geodetic longitude lambda sub e and the what's called the local sidereal time lambda sub g, which is at any instant lambda g is just the angle between the angle to the vernal equinox and the angle to the Greenwich meridian, and that angle changes. It's what's considered to be a constant rate of time as the Earth rotates. That's why it's called sidereal time when it's actually an angle. So the inertial longitude is the sum of sidereal time and geodetic longitude. The geodetic latitude is also shown in the figure, which is phi sub e, and that's the angle in a meridian plane between the equator and the line containing point P. That will be shown a little bit more clearly in a meridian view to be shown on a following slide. And again, if you're referring to spherical geodetic coordinates for locating a position of an object on the oblate spheroid, again we'll show a figure in two views that show a point P that's located on the surface of the oblate spheroid. On the figure at the upper right, you can see depicted, as we just showed also on the previous slide, geodetic latitude is defined or depicted by the symbol phi sub e, and it defines an angle along a meridian plane from the equatorial point to point P. Again, the geodetic longitude is lambda sub e, and that's an angle in the equatorial plane from the prime meridian to the meridian line containing the point P. The inertial longitude is nothing more, as we described earlier, than the sum of the sidereal time and the geodetic longitude. And in the figure on the right, which is a cut through the meridian plane containing point P, it's kind of a side view, if you will, of the figure at the top, you can see the geometry a little more clearly. That's sliced through the oblate spheroid containing point P in the center of the Earth, or the center of the oblate spheroid. And several things I want to show in there for purposes of clarifying what parameters we refer to throughout this presentation. The parameter called phi sub e, as shown there, again is the angle between the equator of the Earth and a line through point P down a local vertical. The geocentric latitude is what I'm calling phi sub c, and that's the angle between the equator and a point directly from the center of the Earth to point P. And the geocentric radius is depicted as r sub p, and again that's the radius from the center of the Earth to the point P. Those terms are important because, or those distinctions are important because we'll have equivalent relationships between rectangular and spherical coordinates written in geodetic coordinates, and also in geocentric coordinates, and it's just personal preference as to which you would like to employ at any particular time in your analysis. In this figure, we'll show some other clarifications of some other terms that we're going to use to define relationships that are used to convert between rectangular coordinates and spherical coordinates, be they geocentric or geodetic. And again, same kind of thing. What we're going to do now, though, is define the position of a point above the surface of the oblate spheroid. And what's shown in the figure to the bottom right depicts just that. As before, we have a point P that's on the surface of the oblate spheroid. We have a point O that's at altitude h above a local vertical line above point P. And that's what's defined as a geodetic altitude. That's the altitude above the surface of the oblate spheroid in a direction normal to the surface at that point P. And so there's several terms that we want to talk about and define what the parameters are called. And as I said, they will be used later in the discussion for calculating some of the geometry that we would need to make those translations between rectangular and spherical coordinates. The radius of curvature in the prime meridian is designated as rho in the figure. And you see what that is. That's basically if you take a slice through this meridian that contains the point P that we're talking about and the point O above the surface of the spheroid, rho is shown as the distance between the little plus sign there, somewhere in the interior of the ellipse, and up to the point P. The radius of curvature in the prime vertical is what's designated as rho v, and that's nothing more than the extension through that radius of curvature from point P to where it intersects with the vertical axis, which is the axis of rotation of the oblate spheroid. The part of the radius of curvature in the prime vertical that's above the equatorial plane, that's designated by rho sub z, and is also shown there. That's just the part of rho z that's above the equator, and that'll be important for doing some calculations as well. Also shown in the figure is a geodetic altitude, as I previously described. That's just the altitude above the local vertical at point P to the object that's directly above it. And then also the geodetic latitude, again, is phi sub e, as shown there, and the geocentric latitude is phi sub c, as shown, and the geocentric radius to a point on the surface is r sub p. All those terms are important because we'll be deriving equations for those, and it's trying to make it clear which parameters we're referring to and how they are actually visualized on the oblate spheroid geometry. Going back to an earlier slide where we showed an expression for the radius of curvature at any point on an ellipse, we just call that on a previous slide. We actually referred to that now as the radius of curvature in the prime meridian at P. And that's rho is computed, as described earlier, as the quantity r times 2a minus r to the 3/2 divided by ab, where in this case the r that we were talking about was the vector from the primary focus up to the point on the ellipse. After some fairly elaborate geometry and calculations and algebra, it can be shown that rho, as depicted in equation 17, can be written in terms of the semi-major axis length A, the eccentricity, and the geodetic latitude, phi sub e, as equation 20. So the radius of curvature in the prime meridian, rho, is equal to A times 1 minus e squared divided by the quantity 1 minus e squared sine squared phi sub e, that quantity to the 3/2 power. Likewise, the radius of curvature in the prime vertical, what's depicted as rho sub v in the figure, can be written as A over the square root of 1 minus e squared sine squared phi sub e. That's equation 21. Finally, that part of rho v that's above the equatorial plane, depicted as rho z in the figure, can be written as A times 1 minus e squared divided by the square root of 1 minus e squared sine squared phi sub e. That's equation 22. So all those will be very important in defining the geometrical relationships between rectangular and spherical coordinates that are going to follow here. As I said, the derivation of equations 20 through 22 is not presented here because the calculations in algebra involved is too involved, but it's not insurmountable to do those calculations yourselves based on the relationships that have been presented so far. Now again, we could show relationships between geocentric radius and geocentric latitude and geodetic latitude as described on this chart. The figure in the upper right is a figure that we've shown before. It's just sliced through a local meridian containing the point P that's located on the surface of the Earth and directly beneath some object above the Earth, the oblate spheroid, point O. And that geodetic altitude is represented by the parameter h. The figure on the right is just an expanded view of the little triangle, if you will, that connects points E, that's the center of the Earth, or the center of the oblate spheroid, point P, the point on the surface, and point O, the point above the surface. And what's shown on those figures needed to define a little bit more clearly, too, what we're talking about. The angle between the horizontal line shown in the lower figure and the line connecting point E and point P is the geocentric latitude, phi sub c. The angle between the horizontal line on the lower figure and the line connecting points E and O is referred to as the declination, delta sub O. And again, as we showed earlier, the distance between point E and point P is referred to as the geocentric radius, RP. The distance between points E and point O is referred to as the geocentric radius. Then it can be pretty easily shown from just simple elementary geometry that the relationship between the geocentric latitude and the geodetic latitude is as shown in equation 23, and that the tangent of the geocentric latitude, phi sub c, equals 1 minus e squared times the tangent of the geodetic latitude, phi sub e. It's also easy to show that the geocentric radius of point P can be computed from the geocentric latitude just computed from equation 24. That is, r sub p is a times the square root of 1 minus e squared divided by the square root of 1 minus e squared cosine squared phi c, where in this case phi c is the geocentric latitude. And that expression, again, will be important, used later in forms of transforming from rectangular coordinates to geocentric and vice versa. Next, we'll discuss how to compute the declination angle of a point above the oblate spheroid. If we define points O, P, and E as defined on the previous slide, where E is the center of the oblate spheroid, point P is a point on the surface of the spheroid directly beneath the point O, which represents the object above the spheroid. And then furthermore, for convenience, we'll also define O, E, and P to be the interior angles of the triangle that's bounded by the distances RC, that's the geocentric radius, RP, the geocentric radius to point P, and H, the geodetic altitude. And then if we apply the law of cosines to the triangle that's shown in the lower right figure, it's pretty clear to see, if you remember your mathematics, that the RC squared equals RP squared plus H squared minus 2 times RP times H times cosine P. Also, it's pretty easy to show that the angle P, as shown in that diagram, also can be computed from 180 degrees minus phi E minus phi C, where again phi E is the geodetic latitude, phi C is the geocentric latitude. And also, by applying the law of sines to the triangle on the lower right, you come up with three quantities that equal each other, and that's sine E over H equals sine O over RP, which is also equal to sine of P over RC. So then, combining these, it can be shown that the angle O can be computed as shown in the equation in the fourth bullet there, that sine of the angle O equals RP over RC times sine of phi E minus phi sub c. Finally, by combining all the information that we've presented so far, you can show that the declination angle delta 0 of some point O above the oblate spheroid can be computed as delta 0 is phi c plus E, where the angle E equals phi E minus phi C minus the angle O. And the angle O was computed directly above. So that finally, summarizing all that, you can calculate the declination angle delta sub 0 is geodetic latitude minus the angle O, where the angle O is merely the arc sine of RP over RC times sine phi E minus phi C. Summarizing the equations shown in this section, the equations that you would use to calculate the geocentric radius RC, the geocentric latitude phi sub C, the declination angle delta 0, and the geocentric radius to a point on the surface R sub P are all shown by equations 23 through 26 on this page. And they were described in more detail in the previous slides. This is just a summary of what's already been discussed the last few slides. Now we'll discuss how do we convert from spherical to rectangular coordinates and vice versa. The figures at the right show a meridian view and a top view plane of some object located on the surface, above the surface of an oblate spheroid, similar to the figures we've shown in the previous slides. The meridian view on the top is just looking, normal to the meridian plane that contains the points O and P. The top view on the bottom of the right is just looking down the ZE axis, or looking down the axis of rotation of that oblate spheroid. The vertical component of the object, which is shown as Z sub E in the top figure, can be shown real clearly to be phi Z plus H times sine of the geodetic latitude phi E. So, knowing the expression for phi Z that we computed a few moments ago, and geodetic latitude phi E and geodetic altitude H, you can compute the rectangular coordinate ZE, which is the distance of the point O from the center of the Earth along the along the Z Earth direction. The horizontal components of the object, what's depicted as YE and ZE in the lower right figure, can be computed as shown in equations 28 and 29, and that's rho V plus H times the cosine of phi E, each of those times either the cosine of lambda E or the sine of lambda E, where lambda E is the geodetic longitude. And again, just summarizing for both these equations what we presented earlier, phi sub V and phi sub Z are as depicted in equations 21 and 22. And again, they're a function only of the constants of the oblate spheroid, semi-major axis length A and eccentricity E, and the geodetic latitude phi sub E. So these equations, 27, 28, 29, would be the equations for converting from geodetic spherical coordinates to rectangular coordinates. We can also convert from spherical to rectangular coordinates using geocentric coordinates and declination, as we described a few slides ago as well. And again, the figures on the right of this slide are similar to the figures on the previous slide, except now we'll show the geocentric latitude phi sub C, the declination phi sub O, geocentric radius RC. So now, given those forms of spherical coordinates, equations 30 through 32 can be used to compute the ECEF rectangular coordinates XE, YE, and ZE as shown in those equations, where the values for the geocentric radius RC and the declination delta sub 0 were presented 2 or 3 slides ago, pages 15 and 16. So once we've computed from the equations on page 15 and 16 the geocentric radius and declination, it's real easy to calculate the rectangular coordinates from them. Now we want to do the reverse transformation. We want to go, assuming we know rectangular coordinates, we'd like to compute the spherical from them. So first we'll convert from rectangular coordinates to geodetic coordinates, that is, geodetic latitude, geodetic longitude, and geodetic altitude. The calculation of geodetic longitude is exact and very simple. That's shown by equation 33 on this slide. Geodetic longitude is nothing more than the arctangent of the YE rectangular coordinate divided by XE. And note that you would need to do a 4-quadrant arctangent for that, so that you get the proper plus or minus 180 degrees, or conversely, if you want to think of it this way, 0 to 180 degrees for longitude. Next, we have to compute the geodetic latitude. Right? It's not quite as simple because there's not a simple closed-form solution for it. There are closed-form solutions available. One is Sofaer's method. Although what you will find in practice is Sofaer's method is very complicated, and it's also very prone to truncation errors, even if you use double precision calculations. A method I prefer is derived from a single pass Newton-Raphson iterative solution of the nonlinear coupled equations. And you might think the exact solution is more accurate than the iterative solution, but actually the reverse is true. It can be shown that at least for some, if not most, positions defined on an oblate spheroid, the exact solution, such as Sofaer's, is not as accurate as the approximate solution, and that's due to numerical precision and round-off, again, even if you're using double precision calculations. And you can show that by starting with spherical coordinates, computing the rectangular coordinates, computing from the rectangular back to the spherical, and then looking at the difference between your computed spherical coordinates and the spherical coordinates you started with. Do that with both Sofaer's or other exact methods, and this Newton-Raphson approximate solution, you'll actually find out that Newton-Raphson, as shown here, is actually more accurate. In other words, it has less error in getting back to your original spherical coordinates than the so-called exact method. So the method shown here is real straightforward. After you've computed the geodetic latitude, which I'll show on the next page, shown as phi sub e, the exact equation for computing geodetic altitude can be computed very simply from equations 34 or 35. First of all, if the geodetic latitude is not equal to plus or minus pi over 2, in other words, you're not at the South Pole exactly or North Pole exactly, then you can compute geodetic altitude from equation 34. If the geodetic latitude is exactly plus or minus pi over 2, in other words, you're at the North Pole or South Pole, you compute geodetic altitude as shown in equation 35. Again, those are exact equations given that phi e is, if phi e is exact, that's an exact calculation of geodetic latitude. Excuse me, geodetic altitude. Now going to the next slide, we'll show how you would compute the approximate solution for geodetic latitude. First you compute just something, I'll call it theta for lack of a better thing, in equation 36. It's the arctangent of ZE divided by 1 minus the flattening ratio times the square root of XE squared plus YE squared. And again, obviously, XE, YE, and ZE here are just the rectangular coordinates of the position you're trying to describe. Then once you've computed theta using equation 36, you compute geodetic latitude as shown in equation 37. The arctangent of ZE plus AE squared over 1 minus flattening times sine cubed of theta divided by the square root of XE squared plus YE squared minus AE squared times cosine cubed theta. And for both those arctangent calculations in equations 36 and 37, a principal value arctangent is sufficient for both. So this concludes part 1 of the presentation, Fundamentals of Geodetic Kinematics. This part 1, Introduction and Definitions, we covered the following topics: mathematical relationships for ellipses, coordinate frames and definition of terms, some of the equations used for geodetic kinematics, and most especially the equations used for spherical to rectangular position coordinates and vice versa. In part 2 of this presentation, which is entitled Implementation, we'll cover the following topics. More of a description of sidereal time, which we touched on a little bit today in today's presentation. We'll also summarize the World Geodetic Standard 1984 standard constants that are used for the Earth and the Moon, coordinate frames that are commonly used for modeling of geodetic kinematics, equations for navigation over an oblate spheroid, calculation of great circle distances, and calculation of the position and velocity of an object relative to planet-fixed frames. So this concludes part 1 of the 2-part discussion about the fundamentals of geodetic kinematics. I hope that you found this presentation to be useful and informative, and I invite you to continue with part 2 of my presentation. Thank you.